Welcome to the presentation of our paper. The topic of this work is on auditing or evaluating the bias of machine learning models when we have access to uncertain or incomplete information. And this will become more clear in subsequent slides. So here is the outline of the talk. I'm going to first motivate the problem using an example scenario. Then I will present the precise mathematical formulation of the problem that we study. This will be followed by a discussion of the main results, and then I will end with conclusions and future directions. So to motivate the problem, consider an example scenario where a bank has trained a machine learning model to help decide whether to offer loan to particular individuals or not. And as a standard practice, in order to do this, the bank would collect a training data as shown on the left, where the rows correspond to individuals and the columns correspond to relevant features for the task at hand, with the last column, capital Y, corresponding to the true outcome for that individual. This training data is then fed into a learning algorithm, which outputs a machine learning model as shown on the right. And now the bank wants to estimate how biased the model is according to a certain metric. And let's say the metric that the bank is interested in is the difference in the true positive rates of the model across two different subpopulations. And here the bank is using race as a distinguishing feature to define the two subpopulations. And as a standard practice, we are going to denote race in this case as the sensitive attribute for the problem. As you might notice, this is simply the popular equal opportunity metric that was proposed by the work of Hart, Price, and Srebro in 2016, and this will be the metric that we will study throughout this work. Now, this is a very common scenario, not just in this bank example, but in general, when testing machine learning models for underlying biases, we have access to a trained model and a particular metric of interest that we would like to estimate. So in this work, we are concerned with equal opportunity metric, but you could think of statistical parity or calibration or any of the other metrics that have been proposed in the literature. Now, what is the bottleneck in evaluating such a fairness metric? The key bottleneck is that evaluating these metrics requires us to have a data set containing both the label and the sensitive attribute information together. So what I mean by that is, in order to estimate the bias, let's say in the bank example, we would need access to a data set as shown on the left, where we have data about a set of individuals, and each individual's data is labeled both by the race of that individual or the sensitive attribute information, and also the true outcome variable y. Now, this is rarely the case, and in practice, data sets often look like as shown on the right, where we rarely have access to both the sensitive attribute information and the true class level information at the same time. If at all, we might have very few individuals that are labeled by both these variables. And what we want to study is how should one approach bias estimation in such a scenario. So this is what we call as the demographic sparse setting, where common data involving the class labels and the sensitive attributes is scarce. And we would like to understand how should one approach bias estimation in this scenario. So a popular workaround to this problem is to actually use a prediction model, which is denoted by H here, to predict the sensitive attribute information for the individuals. Where does this prediction model come from? This prediction model could either involve the use of proxy attributes. So these are maybe other relevant features or attributes in your dataset that you think may be correlated with the sensitive attribute. Or this could involve training a separate classifier on a separate dataset just to predict the sensitive attributes. And the advantage of this approach is that it decouples the data requirement. So in order to train the prediction model for the class label, you only need access to a data set that has class label information. In order to develop a prediction model for the sensitive attribute, you only need access to a data set that has information about the sensitive attributes of the individuals. So the requirement for having common data involving both the sensitive attribute and the class label is removed. But this approach also brings two fundamental questions, which is what constitutes a good prediction model H or a good proxy H? And if you have such a prediction model in hand, how should you use it? How should you go about using it for accurate bias estimation? And these are the two questions that we study in this work. So let me now present the precise mathematical formulation for this problem. And for that, I will have to define certain notation. So I'm going to denote capital X to be the feature space. So these are all the relevant features for the problem at hand. So in the bank example, this would correspond to the credit score and income of the individuals. We are going to denote capital Y as the label space or the true outcome. And this would always take values in -1 or 1. And we are going to denote by capital A the sensitive attribute, which will again take two values, either 0 or 1. So we are going to be concerned with two different subpopulations. Now what we have is a joint distribution Q over these three spaces, X, Y, and A. And for a given label classifier, which we are going to denote by F, so F maps relevant features to a model outcome, we are going to denote the bias of this label classifier as the absolute difference between alpha and beta, where alpha is the probability of the model outcome, or F being equal to 1, conditioned on the true outcome being equal to 1, and the sensitive attribute being equal to 1. And beta is the probability of model outcome equals 1, condition on y equals 1, and the sensitive attribute being 0. So this is, again, nothing but the equal opportunity metric that I discussed before. So bias of Q is ideally what we would like to estimate. But what we have access to instead is not directly the joint distribution. Recall, we are in this setting where access to common data involving the class label and the sensitive attribute is not possible. What we instead have is access to marginals of this distribution Q. So we have access to a distribution Q1 that involves data containing the features and the class labels. And we have access to the marginal Q2 that involves data containing the features and the sensitive attributes. Now what can do is use Q2 to train a classifier H to predict the sensitive attribute. And then we would like to use H to perform bias estimation. And in this case, again, for a given label classifier F, we can define the estimated bias denoted by bias twiddle of F as the absolute difference between alpha hat and beta hat, where alpha hat and beta hat are going to be noisy estimates of alpha and beta. So alpha hat is going to be defined exactly the same as alpha, except that instead of conditioning on A equals 1, we are conditioning on H of X equals 1. Recall that H is the prediction of the sensitive attribute classifier for the true value A. Similarly, beta hat is going to be defined as the same as beta, except that instead of conditioning on A equals 0, we are conditioning on H of X equals 0. And we would like to understand how the estimated bias relates to the true bias. I must mention that in recent years, there have been certain works understanding this setting, where there have been works quantifying the uncertainty in bias estimates under noise. There have even been works studying the effect of noise when training fair classifiers or when incorporating fairness constraints in noisy settings. I'm not going to go into too much detail in the talk, but please see the paper for a more broader discussion of these works. As I mentioned before, what we are interested in is first understanding what constitutes a good prediction model H or a good sensitive attribute classifier H. This is what we call as the perspective of the attribute classifier modeler, the person who's designing the attribute classifier. And there are a few natural criteria that come to mind. One is you could either train the most accurate classifier, just optimize for the accuracy of the classifier, or you could perhaps train the most fair classifier according to some metric, hoping that this would result in good bias estimation downstream. And our first result is to show that none of these actually capture the structure of the optimal classifier. The actual situation is much more nuanced. So in order to demonstrate this, first we perform an empirical experiment where we take the UCI adult data set we train a machine learning model to predict the true class label, and we fix that model, and the true bias of the model is 0.1149. Then we train 7 different classifiers to predict the sensitive attribute for the data points. And these classifiers range from a random forest-based model to logistic regression-based models based on subsets of features to SVMs and neural nets. And then we use the predictions of H to estimate the bias of the model. If you recall the notation from the previous slides, we estimate alpha hat minus beta hat instead of alpha minus beta. And as you can see from the table, the model that comes the closest to the true bias of 0.1149 is actually the one with the least test accuracy amongst all the models. So the test accuracy is not necessarily correlated with the ability to perform accurate bias estimation. And in fact, we show theoretically that the situation can be very bad. So we construct an instance where the true bias of a model is 0, but if you use the Bayes optimal classifier for predicting H, Bayes optimal in terms of accuracy, this would lead to an estimated bias of 1. So this could be very far off. And the message here again is that test accuracy is not necessarily correlated with the effectiveness for bias estimation. So a natural question then is, what characterizes the optimal attribute classifier? And we make some progress on answering this question. So in order to do this, we try to characterize what we call as the distortion factor gamma, which is the ratio between alpha hat minus beta hat over alpha minus beta. And we are not able to characterize the optimal classifier in full generality, but under a simplifying assumption. So the simplifying assumption that we make is that the label classifier and the attribute classifier are conditionally independent when given the true attribute, true sensitive attribute A and the true class label Y. Now, this is admittedly a strong assumption, but nonetheless, it will give us some insight into the complexity of the problem. And in the paper, we do discuss some scenarios where you could expect this assumption to hold true approximately. And we also present experiments with a data set, a real-world data set, where this assumption does indeed hold true approximately. Now, what we show is that under the simplifying assumption, the distortion factor is exactly characterized as shown in the equation here, and it's always lies in the range of 0 to 1, which means that the estimated bias is always an underestimate of the true bias. Furthermore, the distortion factor is characterized by 4 quantities: G1, G2, R, and S. R and S here are properties of the data distribution that we call as the base rates. So R is the probability of y equals 1, A equals 1. S is the probability of y equals 1, A equals 0. And G1 and G2 are the conditional errors of the model when conditioned on y equals 1, A equals 0, and y equals 1, A equals 1. Okay. Now, having this expression for gamma in our hand, we can try to see what maximizes gamma. So remember that under the assumption, since gamma is always in 0 to 1, for us to have the most accurate bias estimation, we would like gamma to be as close to 1 as possible. And here we prove sort of a counterintuitive claim, counterintuitive statement that if the assumption holds, and in particular if the base rates are the same, let's say R equals S, then for a given error budget U for the sensitive attribute classifier, the distortion is maximized, gamma is maximized at one of the extreme points. That is either G1 is 0 or G2 is 0, or G1 is 1 or G2 is 1. What this means is that there are situations where if you have a given error budget to train your sensitive attribute classifier, you should try to completely optimize the conditional error on one of the subpopulations. And this is very counterintuitive to what one might expect to do in practice. And although we prove the theorem for the case when R equals S, the same phenomena also seems to hold true for other values of R and S, as we show in the plots here. So what the previous theorem suggests is it really points to the complexity of the problem of designing a good sensitive attribute classifier. And what it shows is that we really cannot trust standard metrics such as accuracy in order to attach a level of confidence in how good our sensitive attribute classifier might be. And in fact, there could be scenarios where the structure of the optimal classifier could be very counterintuitive. This places even more of an importance into the next question that we study, which is how should one use such a sensitive attribute classifier? This we call as the perspective of the label classifier modeler, or the person who has access to the label classifier also has access to a sensitive attribute classifier and would like to now perform bias estimation. Now there are two ways in which you could try to use the sensitive attribute classifier H or the proxy H. You could either simply use the predictions of H and compute alpha hat minus beta hat, but this could lead to pretty high error in light of the previous discussion, unless we have a very detailed understanding of how exactly H was constructed. The other option is to completely ignore H and directly estimate bias. But this is again not possible because we are in this data scarce regime where we might not have a lot of common data involving YNA. So in order to solve this problem, what we look at is a setting where we want to use as little common data involving YNA as possible and use the predictions of H to as greater an extent as we can in order to perform good bias estimation. And in order to do this, we propose an efficient heuristic, which we call as an active sampling algorithm. And what the algorithm does is it carefully decides when to trust the predictions of H. Recall that we cannot simply trust the predictions of H on every data point. What the algorithm instead does is it creates an uncertainty estimate for each data point using the prediction of H. And based on the uncertainty estimate, it decides whether it wants to query for both the label and the sensitive attribute information for that data point or not. And as we see in our experiments, this algorithm leads to a significantly lower requirement on the amount of common data that's needed. So let me spend some time discussing how the active sampling algorithm works. So the starting point for the algorithm is the following general theorem that we show, which characterizes how the true bias relates to the estimated bias without any assumptions. So this holds in general. And notice that in this case, the true bias is related to the estimated bias via quantities R, S, G1, G2 as before, and there are also additional quantities delta 1 and delta 2. I'm not going to define what delta 1 and delta 2 are, but the way the active sampling algorithm works is by estimating these quantities via computing uncertainty estimates. And the plots here show the performance of our active sampling algorithm as compared to other approaches. So the plot on the left shows the data requirement of our active sampling algorithm as compared to other baseline sampling methods. And as we can see, very quickly, the difference between the true bias and the estimated bias drops to 0 when using our algorithm. The plot on the right shows the sample size that's needed when directly estimating alpha and beta, so without using the structure of theorem 4. And again, as you can see, the data requirement in this case is much higher than what it would be when using our active sampling algorithm. So I would like to conclude now by recapping our broad goal, which was to understand bias estimation in the demographic scarce setting. Our paper has two main messages. One is that the problem of designing a sensitive attribute classifier is a very complex one, and standard metrics such as accuracy are not necessarily correlated with the structure of the optimal classifier. And in light of this, sensitive attribute classifiers or proxies should be used very carefully when doing bias estimation. And we do provide a practical heuristic in order to do this. In the future, we hope that our work will lead to a more deeper understanding of what constitutes a good prediction model or a good sensitive attribute classifier, In particular, it would be interesting to remove the independence assumptions that we use in our work. And it would also be interesting to see if the theoretical analysis leads to new algorithmic techniques or maybe regularizers to select good proxies for sensitive attributes. Thank you.